So the sum of any two sides has to be greater than the third. So if you add any two sides together in a triangle, in order for that figure to be a triangle, any two sides that you add together would have to be greater than the third, right? So for example, I'll show you one that doesn't work. I'll just kind of throw it off on the side here. So let's say you have a triangle that I've labeled 1, 2, 3. All right. So if I label this triangle with sides 1, 2, and 3, this actually could never be a triangle. I mean, just because I labeled it with sides measured at 1, 2, and 3 doesn't mean that it's actually true, right? Because I can't just say, well, these are the sides without any kind of reasonable justification. Because 1 plus 2 is equal to 3. Fun fact of the day. What that really means is that since any two sides must add to be greater than the third, 1 plus 2 is not greater than 3. So this is not a triangle. I'll just use a triangle symbol. All right. So you might look at it and say, well, it certainly is a triangle. Look at it. It's a geometric figure with 3 sides. Again, just because I drew a triangle and labeled it 1, 2, 3 doesn't mean I was right to do so. Right. So really what's happening is that we have a side with a length of 1 and a side of length of 2. If I have a side of length of 1 and a side of length of 2, and I'm using the word of a lot, but there's no way that would create an angle with the base, right? Because if you think about it, you have a distance of 3, right? So 3 units, I'll split it up, just kind of eyeball it. Each one of these segments constitutes about 1 unit, right? So 1, 1, 1, right? If I tell you that I have a side that has a length of 1, so really essentially this side here, right? And you know how difficult it is to rotate in this context, but I'll do it anyway, just kind of rough it. You're looking at something like this, right? That would be a side of length of 1. So I'm essentially drawing it to scale because this side here has a length of 3. All right, a side with a length of 2 would look something like this. If I try to reach that third side, the red side, I'll call it, with the blue side from that black vertex, there's no way I would ever get there. So I would fall short. I actually kind of successfully rotated that, which is shocking. All right. Now, what we do, instead of just kind of eyeballing it, because you look at it and say, well, maybe if I rotated this more this way, and fit, it's never going to cover quite the distance that it needs to cover in order to get there, right? But what we tend to do when it comes to precision in geometry, we use what we call constructions, right? So I'll just, this won't be an exact construction, but I'll give you kind of a sense of what I'm talking about. I'll just copy this side. If I say, again, that, maybe it's predetermined that this is the length of 1, each one of these is the length of 1, I could come up with a side or a distance of 1 unit by drawing a circle with a radius of that, whatever that distance is. All right. So any point on this circumference of this circle would have to be a point that could be the end point of any angle created with a radius of 1. Right, so I could place it anywhere I want along this. Right, anywhere I want. And so I'm just gonna, I'll put it right there. Right. Then I would do the same thing for the other side, except it's gonna go off the paper. So let me just kind of move it over a little bit. That's what my circle normally looks like, and this is what it looks like when it corrects itself. So this is what a circle with a radius of 2 would look like. If I were to draw a line segment, let me fix that. A line segment starting at this center, the approximate center, no matter where I put it around this circle, and no matter where I put the red line or the red radius around that circle, there's never an instance except on the line itself where they would ever actually meet. Right? So there's no way it could ever actually be a triangle. It's not possible. Right? So unless there's overlap between the two circles, you're not going to have a triangle like this, right? So that was, you know, just a quick side example, but that's the idea behind establishing whether something is a circle or not. Right? So from there, we can make a determination of what type of circle we're looking at. Right? So you know, I'll show you the computation first, and then we'll draw the conclusion from there. All right. So if I'm looking at this diagram here with dimensions 9, 12, and 15, they're saying a squared plus b squared blank c squared. All right. The intention here is to have any of 3 possibilities: equals, greater than, or less than. All right. Any of these 3 possibilities could be the sign that exists between the b squared and the c squared, right? So the longest side of the triangle is considered the c value. In a right triangle, that happens to be opposite the 90-degree angle. But if it's not a right triangle, there is no 90-degree angle. So you can't establish the hypotenuse based off its relationship to the 90-degree angle. So we just identify the hypotenuse of the triangle as the longest side, if you happen to know it, right? So I would call this A, I call this B, I call this C, right? So A squared plus B squared, I'm going to figure out what C squared is. A squared is 9, well, 9 squared. B squared is 12 squared. C squared is 15 squared. 9 squared is 81. You chuck it in a calculator if you want. 144 is 12 squared. 225 is 15 squared. All right. 81 plus 144 happens to be 225. So the relationship here is that these are all equal. If a squared plus b squared is equal to c squared, I mean, that's the one that we discussed last time, and it's the one you're probably most familiar with. That would be a right triangle. So a triangle is a right triangle if a squared plus b squared is equal to c squared. But sometimes a squared plus b squared is not equal to c squared, right? So again, we have our 3 possibilities here. We've already accounted for the equal sign. So now I'm down to these 2. The longest side is 10. So that would be my C. Typically, we go shortest side as A, middle side is B, but those 2 are interchangeable, so it doesn't really matter. But I'll call this one A and call this one B. So again, A squared plus B squared, some relationship to C squared. All right. So 8 squared plus 9 squared, some relationship to 10 squared. 8 squared is 64. 9 squared is 81. 64 plus 81 is 145. 10 squared is 100. So we have a relationship where a squared plus b squared is greater than c squared. All right, and so that would be an acute triangle. right? So acute. A triangle is an acute triangle. It's adorable. Yeah. Acute as in less than 90 degrees. If a squared plus b squared is greater than c squared. Right. Now, common sense tells us, or well, maybe not common sense, just
Pass it.
whoa.
Pass it.
Hey. I jumped 10 feet out of my seat. I don't know about the rest of you. That was fun. Let's go with the old mute unless you have a question deal, I guess. Or, you know, spontaneously yell stuff. That's fun too. Right. So a triangle is a, well, right triangle, acute. I mean, that would only leave obtuse, and that would only leave a less than symbol. But let's play it out here. So a squared plus b squared, c squared, right? The longest side is your c, the shortest side is the a, and your b. But again, a and b are interchangeable, so it doesn't matter. Right? So 8 squared plus 12 squared result 15 squared. 8 squared is 64, 144, and 225. 64 plus 144 is 208. 208 versus 225. 208 is less than 225. Right. So that would be an obtuse triangle. So we can demonstrate that a triangle is obtuse if we show that the two smaller sides, when applied using the, you know, a variation of the Pythagorean theorem, those two sides have squared values when added together is less than the squared value of the third side. Right. So, you know, it kind of goes hand in hand with what we talk about in terms of geometric proof. You know, we don't want to just say something is because we think it is, it looks like it is. We want to show that it is always, right? But these relationships help us to prove that the triangles have these particular characteristics. All right. So the examples that follow.
Ramona, you need to mute your mic, please. Thank you.
Okay, thank you. Sorry.
Professor, could you just repeat that last part that you just said? You said the two with the obtuse, two smaller sides have a square value added together is less than, and then I didn't hear.
The squared value of the third side.
Thank you.
Yeah, no problem. All right, so the examples that follow are all kind of geared along the same thing. Sometimes you're just given numerical values, and you can see some radicals are involved. That, you know, sometimes radicals aren't involved. But either way, anytime you're talking about squaring values and those values are themselves radicals, that's kind of like the best possible outcome, right? But the thing is, when you look at something like number one, a question like number one, it is kind of important that you're able to identify which one the largest side is, right? Like three lengths of a triangle, we have radical 6, 3, and radical 15. So I would just pop those in. If I'm not sure, pop them in. I mean, 3 is 3. We don't have to worry about that. But pop them in and see which one the longest one is, right? The radicand of 15, you know, just because 15 is bigger than 3 doesn't mean that it would give a value that's overall bigger than 3. So for example, if this said radical 6, 3, and radical 7, you know, radical 7 would look like it's probably bigger than 3, but radical 7 is not bigger than 3, right? So double checking in the calculator is the way to go. But once you've identified the longest side, the longest, that becomes your C. All right, so we would apply a squared plus b squared something c squared, because we don't know necessarily that it's going to be equal. Right? Once we've identified the C, either of the other two could be A or B. It doesn't matter which is which. Right? So I'll call this, just for the sake of consistency, I'll call this one the A, and I'll call this one the B. All right, and that's because radical 6 is 2 and change, that's smaller than 3. Right, so I would take radical 6, square it, 3, square it, and then I would have radical 15. I'm going to square that too. And then see what comes of it. Just trying to be consistent in the color. Right? Radical 6 squared, whether you do it in your head or in your calculator, that's going to give you a result of 6. Right? And that's because the power of 2 and the radical cancel each other away. Right? If you're not sure, you got a calculator, type it in. Right? Radical 6, close it up and square. Right? Shows you a 6. Then 9, radical 15 squared, that's going to be 15. Right? But again, just in case you're not sure, pop it in. You get the 15 anyhow. All right. Now 6 plus 9 is equal to 15. So this is a right triangle. Right? If it were less, it would be obtuse. If it were greater, it would be acute. Right. I'll grab number 2 in a minute, but number 3, I can keep number 1 right on the screen here. So kind of the nicest one, you know, and don't let appearances deceive you, because you look at this and you say 12 inches versus the square root of 119 inches. That must be really big. Right. So square root of 119 is a little bit less than 11. Right. So the longest side here is 12. So that would be our C. Right. Now, if you're careful with the diagram, where possible, anytime I include a diagram, I try to include a scale drawing. So the side that looks the longest usually is the longest, except when I go out of my way to state that no, this is just a generic looking triangle. But if I do something like this, then the one that looks the longest is the longest, except they kind of look like they're pretty close in length. They look kind of like a tie, right? But this one is clearly the shortest, so we'll call that A, and this one would be B. So A squared plus B squared blank C squared. Looks like a trapezoid. That's next to you. Still a trapezoid. Save that for later. So we're looking at four squared, radical 119 squared, and 12 squared. And we want the relationship between those three things. So 4 squared is the easy one. That's 16. Well, radical 119 squared is also the easy one, because you take a radical and square it, it's just whatever's under the radical. So 119. 12 squared is 144. So we're looking at 135. 135 versus 144. All right. So 135 is less than 144. So this one would be obtuse. You're being obtuse. right? So that's an obtuse triangle. You know, at first glance, it kind of looks like, I'm not really sure. It's like right on that borderline. That's the thing. Like, unless a triangle has this little marking here, you can't assume it's a right triangle because sometimes it could just be like a quarter of a degree off. And it's not a right triangle. You know, if it's an 89.75 degree angle, yeah, it's damn near a right triangle, but it's not a right triangle. Right? So we'd have to keep that in mind. Right? So this might be ever so slightly an obtuse triangle, but it's still obtuse. It still satisfies the rule of being obtuse. Right? Something a little bit more straightforward, number 2, 12, 9, and 8. 12 is clearly the longer one. So that's my C. So again, a squared plus b squared is equal to c squared. I said of course I have. A squared plus b squared blank c squared. All right, so 8 squared. Let's have a marker on. Plus 9 squared. And 12 squared. All right, 8 squared is 64. 9 squared is 81. 12 squared is 144. All right, so we're looking at 145, which is ever so slightly larger than 144. All right, so that's just barely acute. All right, so that's an acute triangle, but just barely. Page there, so fix that. Oh, triple wall. Right, it's still acute because a squared plus b squared is greater than c squared, but I mean it's not by a heck of a lot. Trying to think of a way to construct this quickly just to show you. I'll do it later. But there is a way that I can demonstrate how you can create the triangle with the particular dimensions. But like I said, I'll show that in a little bit. All right. And then number 4, again, the longest one, which one is it? So if you're not sure, pop it in. Radical 11 is 3 and change. Radical 7 is 2 and change. So my longest side is the radical 11. Not right. So that's my C. So a squared plus b squared blank c squared. So rad 7 squared, 3 squared, and then rad 11 squared. So squared, squared, squared. So we have 7 plus 9 is 11. Oh, what's the relationship to 11? 7 plus 9 is 18. 16. 16 and 11 has a relationship where 16 is more than 11. So that would be another acute triangle. Aside from the fact that it actually looks like an acute triangle, the math bears it out too. All right, so we could verify, and I'll say fairly quickly, but there's some number crunching that goes on. There always seems to, it's math. There always seems to be some number crunching. All right. Let me see really quickly if I can think of a way to prove this to you using Geogebra. I'm just gonna pause this for a sec. This will be the subject of an assignment down the line, but coming into an assessment, I don't want to overdo it. But what we can do is we can determine particular lengths based off of construction techniques, right? But we use circles, all right? So what I can do here is I can draw a circle starting at C and going to D, and then a circle going from D to C, right? And what that does is it gives me two points here. And if I connect those 2 points, those two points will actually bisect that given line segment, right? So what I would do here is I'd plot a point at this location and one at this location, and then connect them with a segment. All right, so now I've split it up into a distance of, originally it was three units. Now it's 1.5, 1.5, right? So I've broken it into half units, right? So any point that exists on this curve and any point that exists on this curve could create a triangle, right? So if I connect, so for example, if I went this route, I'd get a triangle. All right, so I could do that. Or I can plot a point, for example, let's say I plotted a point here. Let me use my polygon tool. I can create a triangle, right? Any point on this curve and on this curve would get the job done, as long as they overlap, right? I could also kind of shorten one of them. You know, instead of going all the way from, I went from C to D, but what if I wanted to go, you know, maybe just from D to a little bit left of D? You know, that would give me a point, right? So I could do that. I can take this point here and make a triangle out of it, right? Because I have two overlapping circles. Now, if I don't have two overlapping circles, right? So let's say I start off with a circle centered at C, and I only go out a little bit. And then I go, same deal, starting at D, and I go out a little bit. I can plot points wherever I want on either of these two circles, but there's no way I can ever make a polygon. I mean, I can make a polygon, but I can never make a triangle out of it, right? So I can connect this to any point along the circle, and it'll go wherever I want it to go. I can connect this center to any point along the circumference of the circle, and that'll go wherever I want it to go. But they would never meet. All right, let me just hide these things real quick. All right, so no matter where I put this, it's never gonna connect with this point over here to make a triangle, right? The only way that that would happen is if the two circles overlap with one another, right? So if I showed the example like that, but let's say I create another circle that does overlap. Now, wherever that point is, undo. I'm just gonna kind of move that G out of there, kind of distracting. All right, but wherever that point is for, I'll call it F, there will be at least one instance where it corresponds with the radius of the other circle. So I can connect based off of that radius and come up with a triangle. But it's kind of weird to think about it because you're basically using knowledge of circles to come up with the definition of a triangle. Kind of strange, right? But that's really the visual of what I was talking about before, right? So it takes a little, it's a little mind bending, but it takes a little to get used to. But once you do, it starts to make an awful lot of sense. Two triangles are said to be in proportion if at least two pairs of corresponding angles are congruent. Two triangles are proportion. If two triangles are in proportion, they are similar. Therefore, two triangles are similar if at least two pairs of corresponding angles are congruent. Okay. You can also think of it as if they look the same, except one is smaller or bigger than the other, then they're probably similar. Right? We just want to be able to prove that they are. Right? And because honestly, I mean, in terms of real world applications of geometry, you have a need to discuss congruence, but similarity comes in handy in a big way. And I'll talk to you more about those applications as we go forward. But for now, it's really just a matter of using that information to help us make a determination of whether two triangles are congruent. I could actually go back to the logic of it. Two triangles are said to be in proportion if at least two pairs of corresponding angles are congruent. So that would make this my premise. At least two pairs of corresponding angles are congruent. I can call that P for premise. And then this would be the conclusion. So it's kind of written backwards, but this is saying P implies Q. If two triangles are in proportion, they are similar. All right, that's just a repeat of this previous statement, except it's as a premise now. Two triangles are in proportion. So that's Q implies they are similar, that's new. So we'll call that R. So Q implies R. So from this, we could apply the law of syllogisms and state, so therefore, P implies R by the law of syllogism. All right, the case where if this, then that, if that, then something else, then it's if this, then something else. Right? It's like the Q represents the way station, bridging you from P to R. Right? So P represents at least two pairs of corresponding angles are congruent. R represents they're similar. So what we just proved here is if two pairs of corresponding angles are congruent, then the triangles are similar, which is what they say in the therefore. Two triangles are similar if at least two pairs of congruent of corresponding angles are congruent. Right? So the logic gets you there. Right? So the conclusion comes from the logic, not just from just figuring that must be how it works out. Right. So here it says, or at least in the first example, show that the triangles are similar, then find the value of X. All right. Well, they're similar if you have two pairs of corresponding congruent angles. Well, I have one here, one pair, angle G is congruent to angle J. Right. And then we have another pair. It's subtle, but it's there. These two right angles. Do that in blue. So angle H is congruent to angle K. K. They didn't say to prove it. They just said show it. So I'm just making a statement. I'm not making a whole statement reason table kind of deal. All right. So the triangles are similar. So triangle GHI is similar, that's the notation for similar, a little tilde, to triangle JKL. Okay, so that's great. Now, if two triangles are in proportion, they're similar, right? If two triangles are similar, then at least two pairs of corresponding angles are congruent. If at least two pairs of corresponding angles are congruent, then the triangles are said to be in proportion. All right. So when I say something is in proportion, it means that we have consistent ratios from side to side. So for example, based off of the orientation here, this side corresponds. Let me use a highlighter because that looks pretty awful. This side here corresponds to this one here, so we can make a ratio out of that. So I could say 52 meters to X meters. And I could also make a ratio out of these two sides. I would make a ratio out of the other two sides, but I don't know any information about those. So I can make a ratio out of 20 meters to 5 meters. Now, if they're in proportion, the ratios will remain consistent. As in, whatever this ratio is, that'll be the same over here. Right? So I could set them equal to one another and solve. Right? And you could solve it, in a variety of different ways. You can cross multiply, you can simplify. I mean, there is an old algebra trick, and it's a good one. You can, in a proportion, so fraction equal to another fraction, you can swap the diagonals in any way that you want, as long as you only swap the diagonals. So I can take, because it's geometry class, we don't want to get bogged down too much with the algebra, but we can swap and we can group. So I can swap the X with the 20, but even before I do that, M divided by M goes to 1. They're units, but it's still treated like a variable, right? M divided by M goes to 1. So it makes it a pure ratio. 52 over X would be 20 over 5. I can now swap the X with the 20 and make this 52 over 20 is equal to X over 5. All right. I can also group the 5 with the 52. So as in taking this and shooting it on up with the 52. That saves you a whole lot of algebra, because this is basically saying 5 times 52 over 20 is equal to X. So you can make a fraction out of that. Desmos, 5 times 52. You have 20 on the bottom, and you get a result of 13. X is equal to 13. So 13 what? 13. So X is getting replaced with a 13. The units would be meters because it's XM, X meters. All right. So, but if we're just looking for the value of X, they said find the value of X. X is 13. The length of the side is 13 meters, but that's not what they asked. They asked for what X was. Right, but that's the cool thing about proportions, is that you can swap diagonals, you can group them, you can do a bunch of things. It makes life a whole lot easier. Right, you just got to set up your initial proportion correct. If you do that, then yeah, you've already won. I'll say most of the battle, to be fair. Right. So then battle. Let's make battle the word of the day. Oh, I like to do 2 words in a day these days. So it'll be the first word of the day, battle. BATTLE, like Battle Avenue in White Plains. All right. So that would be the first word of the day. Yeah. So the second example here, show that the triangles below are similar. All right. Now that this is a subtly different question because it's not really asking us to solve anything. It's asking us to demonstrate that the 2 triangles are similar to one another. All right. Well, I already have one piece of information. Actually, I kind of have everything. Because very nicely, I mean, they were super kind in this question, wherever they are. They put little arcs for us. They're basically telling us that this is congruent to that. This is congruent to that. So very, very nice of them, right? But let's pretend we didn't recognize that. If we could demonstrate that the triangle is in proportion, then we will have shown that the triangles are similar to one another. Right? So what I would want to do is identify the longest side, right, in each case, because those should be in proportion. The shortest sides should be in proportion, and the middle side should be in proportion. Right? So we have the shortest, middle, long, shortest, middle, long. All right. It helps to label it up because when they start playing around with the orientation, it can get a little dicey. All right. So my shortest side, I can write as a ratio of 450 inches to 675 inches. My middle ratio, let me highlight that. My middle ratio, that's going to be 600 inches to 900 inches. You can go whatever order you want as long as you're consistent. So if you want to go big to small or small to big, it doesn't make a difference. Up, highlighted the wrong 6 to 9. And then lastly, it would be 750 inches to 1125, also inches. I don't really go down the road of asking trick questions, at least not on purpose. But the only way I could make this a trick question is to change the units somewhere along the lines. You know, like instead of saying 900 inches, I'd say like, I don't even know what it would be. Like 25 yards. You know, I wouldn't do that though. So what I want to do is I want to reduce each one of these fractions and make sure that they're all equivalent. They should all be equivalent, making the triangle in proportion. All right, so I type in the fraction, it gives me a decimal, and in Desmos, I just tap on that little fraction icon, and it'll convert it over into simplest fraction form. All right, again, the inches, the units cancel away. IN divided by IN goes to 1. All right, so then 600 divided by 900, also 2/3. 750 divided by 1125, also 2/3. All right. So if all 3 sides are in proportion, you could say the triangles are in proportion. Therefore, the triangles are similar. And little tilde symbol again to represent similar. Similar. All right. So a couple of little twists on the same general idea. You know, nothing too crazy, but it's the kind of thing where, you know, flash back 10 minutes ago, you see these questions, you know, you see these questions, like, what on earth do I do? You know, after you see the instruction, the demonstration of how it all works, it should make sense. But, you know, at first glance, it's understandable if it doesn't kind of jump off the page at you as something obvious. All right. We'll do one more, and then we'll take a break. All right. I always get these calls from NYU that I don't ever want to answer, because then I'll have to tell them that I'm still paying my student loans. So stop asking me for money. Like, I'm still giving you money, or I've given you enough money to the point where, let's see, 24 years later, I'm still paying off the loans. I don't want to give them more money. It is what it is. At least gas prices aren't out of control. Oh wait, all right, we're subject. In the figure below, there are two distinct triangles that are overlapping. If they are split up, we will have two triangles that are in proportion and therefore similar. I tried my best to create a diagram that would make some kind of sense. But if I look at, let's say we'll call this triangle ABC. And I'll throw in a little point here. We'll call it D. And I'll call this one E. The bigger triangle would be ABC. That little triangle, that it shares a side, right? The AB would be in proportion with DE, but DC shares a side with AC. So DC would be in proportion with AC. And these would be measures. Right. So then the same would be true on the other end, where I would say BC and EC would be in proportion. So I'll say EC on top, little guy on top, and the big one on the bottom. And then the bases would be in proportion with one another. Right. So AB and DE, but again, the little guy on the top. So the measure of DE in proportion or as a ratio to AB. All right. So all of these would hold true for overlapping triangles. And you can see in the examples below, it takes on different forms, you know, but the hope is that you won't always have to split up the triangles in order to make it obvious which ones are, you know, the similar sides and so on. All right. But just to at least get it started, let me show you. If I take this triangle, I'm just going to rewrite. I'm just going to pull it out. I got that triangle there. And then let me get a little guy over here. I'm going to put that over here, just for now anyway. I'll resize it in a minute. But the dimensions of the little one would be 6 and 4. The bigger one, well, the base, let's put this down here for a second. The base is 10. The vertical side is Z, a little crosshatch in my Z. These two triangles overlap with one another. All right. And the reason we can say that they're similar is if you think about it, they must have corresponding congruent angles. Right? Because one of the angles, one pair of angles are the same. It's the same for the small triangle as it is for the big triangle. Right? So this angle here is that little vertex angle for the small one, but also for the big one. All right. Now, it's kind of debatable in terms of the other ones. You know, it's somewhat harder to tell. You know, like these are congruent, definitely. But the rationale for why they're congruent is a little bit less straightforward. Okay. So you get into things like parallel lines. You know, that's a possibility. If two parallel lines are cut by a transversal and the alternate interior angles are congruent. You know, so you have, you know, things like that that you can rely on. But you also have just the ability to solve for different sides within a triangle, which tends to be somewhat cumbersome, but it works out. You know, it takes a little doing, right? But the relationship that exists here is that these sides will be in proportion, right? I know we're going to lose a little bit of the size relationship, but I'm going to reduce it down just so it doesn't take up so much space. But from here, I can now say z over 4 is equal to 10 over 6. So I went big triangle with small triangle, right? Again, as long as you're consistent, it's fine. All right, I'm going to use my little proportion trick. Diagonals are interchangeable and groupable. So I'm going to take that 4 and shoot it on up there with the 10. So this would be the same as saying z is equal to 4 times 10 over 6. Now that's 40 over 6. It's not going to be clean. The best you could do is get a simplified fraction out of it. So 20 over 3. All right, but the hope is that you'd be able to do that without pulling the two triangles apart. Right, but sometimes in order to visualize it, you kind of have to. You know, it's part of the fun, I guess. Right, because in this triangle, knowing that you're taking the ratio of this side to this side, it's kind of weird initially, but if you pull the two triangles apart, you take this one, you know, it's not perfect, but it'll work. And then take this one. No, get over here. Get over here. So you think about, well, what would this side have to be? Right. So you'd have vertical of x, horizontal of 12. Vertical of x, horizontal of 12. And then over here, if you pull up this one, you're looking at vertical of 32, horizontal. Well, the horizontal would be the 12 and the 6 together. So 32 for the vertical and 18 for the horizontal. So then I can create a proportion out of that again, with the idea being consistency. So I'm going small to big for the horizontal, so 12 over 18. Then I'm going to go small to big on the verticals. So x over 32. Wherever possible, when I'm developing my proportions, I try to arrange it so that the x variable is on the top of the fraction. It just makes life a little bit easier. All right, but I can regroup here. Take my 32, swing it out up to go with the 12. And we would be looking at x is equal to 12 times 32 over 18. And then you can crunch that in the calculator. Again, decimal value, so kick it over to fraction form. You're looking at x is equal to 64 over 3. So yeah, it takes a little doing. It's not the easiest thing in the world, but it is manageable. There is, like I was saying before, there is some information that's kind of necessary, and that has to do with these two sides being parallel to one another, right? So, you know, it wasn't mentioned in this problem, it's kind of a typo, but let's say, for example, let's say it wasn't like this. And I'm not making a new problem, I'm just showing you what it would be like in it just very quickly. Let's say instead of going straight up vertical, it went off on an angle. Then these two triangles would not be in proportion. Because even though you'd have these two angles being congruent to one another, I could not say that this angle is congruent to this one. I could not say that this angle is congruent to this one, right? So that would mess everything up. So there is an assumption here that these two angles are parallel to one another. So we represent parallel by putting little arrows along the line. So these two are parallel to one another, which allows our parallel line relationship to hold true. There, I mean, it was a while ago now, but if you remember, if you have two parallel lines and they're cut by a transversal, our short version of the rule was if the angles look the same, they are the same. All right, so this angle would be the same as this one, the same as this one, and the same as this one. Most importantly, this angle would be the same as that one. All right. So we could then conclude that this angle here would be the same as this angle there. We already knew that since this angle here is overlapping with that one, they would have to be congruent. And we have enough to say that the two triangles are similar to one another, which allows us to do this proportional stuff to begin with. All right. So there's a lot of stuff that's kind of going on behind the scenes, but you know, it's one of those things where it's like, you know, you find yourself proving everything from the ground up, and it sort of kind of takes away from the fun a little bit. But it is sort of necessary to talk about it at least once. We'll get into the proofs in a little bit after the break, but at least for now, I just wanted to give you the quick explanation for why we're able to do these things the way that we are. All right, so let's pause for a little bit, about 5 minutes, and then we'll pick up from there. So I'm gonna resume recording. So right triangle similarity. So a right triangle can be broken up, if you drop an altitude, into two other right triangles, each of which would be proportional to the original triangle. Right? So it's kind of mind-bendy to think about that. But if you start off with just an ordinary triangle, right triangle, so this one right here, and draw an altitude. All right, altitude as in it forms a right angle with the base. All right, so that would be this. Then these triangles, so this one here and this one here, would be in proportion with the original triangle. All right, so there's a lot, to use a cliche, there's a lot to unpack there. So let me grab the original triangle here. ABC, well, ACB the way I drew it. I'm just going to pull that out for a sec. All right, it's got angles A, C, B. All right, and sides, well, A, B, C, because we denote the side based off of the lowercase of the angle that is opposite. All right, so lowercase b, lowercase. All right, so just pulling that from this triangle over here. All right, so all three of these triangles are in proportion, all right, which means that I can create a proportion from A to B over here. I can create a proportion from F to H, from H to E. And all of those ratios. I'm sorry, I said proportion. I can create a ratio for each one of those, and all of those ratios would be equivalent to one another. So I could start off with that. All right, so just focusing on these two. I can say H over E is equal to, so I got H over E, so this side to this side, is equal to F over H which would be equal to A over B. That looks pretty terrible, so I'm going to erase it. So all of those ratios would be equivalent to one another. But we want to think about what that means in terms of the original structure, the original triangle. So if I'm looking at H over E, so that would be these two segments. And F over H, that would be these two. It's basically saying that we can create a proportion out of these three sides. But notice how we have one side that's repeated. It's acting as one side of one triangle. So it's acting as a leg of one triangle and also a leg of another triangle, right? So that H is the horizontal leg for one triangle, but it's a vertical leg for the vertical leg for the other, right? Then we have AB. So AB, the ratio, that would be this one to this one. Right. So that gets kind of a little messy because it's like, well, what are we showing here? We just highlighted everything. So if I duplicate my diagram, so I'm actually going to do that a few times. I'll just show you real quick. I'm going to pull this out for a second. Based off of this trio of ratios, I can come up with a couple of different diagrams. So I have the, oh, sorry, moving on me. I have the first one we just talked about. Let me redraw. So I have H, and E, in the other order, but these two sides in proportion along or in ratio along with F to H. All right, so that's that. Out of this trio, I can say H over E is equal to F over H. All right, and that leads to this diagram. All right. I can also say that H over E is equal to A over B. Because any pair of values from this trio would be equivalent, right, in ratio or in proportion to one another. So H over E again and then we'd have A over B. Trying to figure out how to get that without coloring it in. Okay, better not good. Right. So that's something that we could say. We could also say, let me shrink this down. That would be a second ratio. We could also say, why is this not moving? I need to move images. That F over H is equal to A over B. All right, so here's my A and my A and B. And here's my F and H. It's doing it. All right, I'm just gonna take that out. Undo. Now you turn off images. Take this out, delete it. Turn back on images and bring this back in. And it's all production. And so we can come up with those ratios. But we're looking for probably a more practical way of handling this because it is getting out of hand. You know, that's only just looking at the relationship between those two triangles. Right? We haven't really looked at it in relationship to the whole. I mean, we kind of have, but nowhere in here do we have side C and how that factors into anything. You know, so we could have a whole fresh set of triangles that come into play if we're not careful, right? So what we want to be able to do is kind of say unfurl, but really just kind of look at the triangles and just get a sense of what the corresponding congruent angles are so that we can go from there, right? So if I'm looking at, for example, the first example on the next page, for example, the example, I can break that apart, but I would want to make sure that I'm breaking it apart in a reasonable way, right? So I want the sides that are in proportion to one another, and then from there we just kind of hopefully have what we need. If not, then we would, you know, maybe look at different triangles. But if I take one of these ratios, you know, I'm kind of rolling the dice because maybe it's not one of those ratios. There's a ton of different ratios that come into play. So we want the most efficient way to go about doing this. All right. So I look at what I have. So I have an entire triangle, and I know all three of the triangles will be in proportion to one another. All right. So I'm going to do my best to approximate. So I know that I have a right triangle with whose base is 16. It's not a whole heck of a lot of information, but it's something, right? I have a triangle over here, a right triangle, and here I actually know a little bit more. Dimensions x by 7, also right angle. And then I also have another right triangle here. X by 9. All right, so I look at the three possible triangles that I could have, and I say, okay, well, which one is relevant and which one is not? Well, in this case, we have two that are relevant, we need to, and one that is not. Right, the one that has minimal information is really not telling us anything, right? Because I can't make a proportion out of that because I don't have a variable, I don't have another number. There's nothing going on here. So that big triangle, that might as well just stay back where it came from. Right? Just leave that back up there. Right, that it's part of the fun, but it's not really contributing. Right, so now I have these two, and I would want to think about how I could arrange these so that I would have a proportion. Well, they need to have the same orientation, right? So there's two ways to do that. One, I mean, I guess I'm kind of guess and check, but that's really not really rigorous. So instead of that, we could actually rotate our triangles so that they're facing the correct way or the same way, right? So I can take this triangle and rotate it so that it's facing this way and see what that gives me, right? Well, what it gives me are two triangles that, you know, they kind of look, well, no pun intended, they look similar to one another. That's the idea, that they would be in proportion, right? So if you were to change the orientation, yeah, this one's facing the wrong way. If I go that way, or if I go that way, no help, you know, go right back to where I started, you know, over here. But if I orient it this way, the right angle's on the left-hand side and we're in good shape, regardless of how small or big it's supposed to be, because I always lose that as I move it around. It's still going to have that similarity concept or component, right? So now I can put it in proportion. I know the 7's out of whack here, but I kind of do that for effect. So I could say 7 over x is equal to x over 9. Right, and again, we can do the whole regrouping thing where we take the bottoms and just shoot them on up to the top. So 7 times 9 is equal to x times x. So 63 is equal to x squared. And that's where our radical skills come into play, because if I take x squared equals 63, I want to get x. I'm going to take the square root of both sides. I'm going to have to break down that radical 63. All right, so on the left, the square root of x squared just becomes an x. But on the right, I have to break it down into the product of a perfect square factor and something else. All right, so, oh man, I'm 50-50 as to whether or not I remember to post this. I'm just going to take a quick look. So I created a calculator for simplifying radicals. It's a question of, nope, totally forgot to post. All right, well, I'll show it to you now and then I'll post it up later. But I created one for simplifying radicals. All right, so if you struggle with simplifying radicals, this might be helpful. Well, it should be helpful. So the A, you see I have a slider for A. That A represents the radicand. And again, a radicand is the number under the radical. The second column gives you a list of perfect squares. The second and third columns give you the values that multiply to your A. All right. So if I look at my table here, I created a whole table and everything. Very, very fancy. So what I'm looking for as a radicand is 63. I want my radicand to go to 63. If I have trouble getting it to land on 63, I just type it in. And then I now have a list. My second and third columns are all values that'll multiply to 63. 1 times 63 is 63. 4 times 15.75, take my word for it, will multiply to 63. 9 times 7 is 63, and so on. And I have, you know, a very lengthy list, but it doesn't take too long before you see the one that works. And the one that works is the one that has a whole number value in the third column. All right, so 9 and 7 are the perfect factors of 63. The square root of 9 is 3, and the square root of 7 we're stuck with. So we would have x is equal to 3 times the square root of 7, or 3 radical 7, we say. All right, so like I said, I'll get this up on Blackboard. I just honestly, I mean, I could say I forgot, but that goes without saying. I swore I did it in my mind. I thought I did it, but I guess I didn't. I mean, I know I didn't because it's not there. All right. But really, you can see here the skill of simplifying, solving, and all that stuff. That's important, but you need to be able to get the triangle unfurled into a useful similar triangle. All right. So looking at number 2, the orientation is different, but it's the same concept. I'm going to grab every right triangle that exists in this triangle here, the triangle within a triangle. It's not going to be perfect, but I'll grab that one. I'll grab this one. Okay, screwed that up. Bring it in a little. Let me fix this. Make it a little easier. There's another one. Now, I should also take the dimensions with it. All right, so this one has dimensions of X and nothing else. So just X. I mean, it has a dimension, I just don't know what it is. We can figure it out, and I'll show you that in a minute. But for now, I'm just going to say I don't know what it is. So we have X and 9. Pull that one out. And then we have the whole shibbigity bangity boom. All right. So this one, the big boy, I don't know the vertical side. I don't know the horizontal side. I do know the hypotenuse, which is wonderful, but I don't know anything else. So that's not going to be helpful. And so I'm going to leave that alone. Now, it seemed like I didn't know enough about this triangle because they didn't tell us this side here. Because again, that's what we're looking at. But if the whole side here is 25 and the distance from here to here is 9, you think about it, it's like, all right, I got to travel 25 feet. I've already traveled 9 feet. How many more feet do I have to go? All right, so that would be 16. And 16 plus 9 is going to give you the 25. Right, so that surprisingly ended up being something that was useful. It didn't seem like that initially, but it worked out that way. Right, now it's just a matter of getting this to match up appropriately. All right, so I need to get this in proportion. Now, it takes a little bit of a trained eye, but the more experience you get with it, the easier it is to see which sides are in proportion. Until you do that, you start rotating the paper. I mean, if you have an app, that's great, but if not, you start like turning the paper and tracing it, and there's a lot of stuff going on there. There are shortcut rules, but I feel like that takes away from it. Right, so if I rotate this so that the right angle is in the same position for this figure as it is for the other, then I would have what I'm looking for. The only thing I got to be careful about is not to write a 6 instead of a 9, because when I rotated the 9, it's starting to look like a 6. Right, but I have a proportion that would be X over 9 is equal to 16 over X. Right, and so same trick, take the bottoms and multiply them by the tops. You're going to get X times X, which is X squared. 9 times 16, 151. Why did that look? Why did I blank on that? I don't know. 144. Okay. I don't know why I thought it was 151. Oh, because I subtracted 9 instead of 16. Okay. That was more for my own personal pride. So take the square root of both sides. The square root of 144 is going to be 12. So you get X is equal to 12. All right, but it's very visual. It's kind of weird. You look at it like, well, this would all be really easy if I could just rotate my diagrams like you can. And again, you can do it on paper. It's just, it helps to have kind of like a thinner piece of paper, you know, like hold it up to the light and kind of turn it around. But, you know, the visuals here, I think, kind of make it seem a little bit easier. All right. So, you know, it's just a question of what the relevant pieces are. You know, and it's not always the easiest thing to see, but you know, the more you maneuver the diagrams, the easier it is to get at the information, relevant information. So again, in every triangle, any instance where you have a right triangle where they drop an altitude, you'll have 3 triangles that are in proportion. This one, and then, you know, the whole shebang, the big boy. Right. So your first step is to try to figure out what's relevant. That 6 radical 85 is not really 100% clear, but that's supposed to be the vertical. And that's this side here. Right. So each one of these 2 line segments is 6 radical 85. So there, and also for the other one. I'm just going to kind of offset it a little bit so they don't overlap. 36, that's this little guy here. So 36, we have a right angle. This whole distance here is x, so that corresponds with this. Right? But then we don't know anything about this side, and we don't know anything about this side. So another instance where the big triangle is not relevant. Right? Because we don't have enough information about it. It doesn't seem like we have enough information about anything else either, but we actually do, because you know, just like we did over here, when we figured out that this was 16, because one part of it was 9 and we subtracted it from the 25, we could do the same thing here. We're just doing it with x, right? If there's x units across the way and you've already traveled 36 of those units, to get the rest of the way, you'd have to go x minus 36. And if you think about it, like what would you get if you added 36 and x minus 36? You get x. So this side here has to be x minus 36. Right? It's just a matter of getting the right orientation. So I got to turn one of my triangles. We want this right angle to be consistent in the same position between the 2 triangles. So I'm going to turn this one. So then I would be looking at 36 over 6 radical 85. And 6, I know it was terrible, but 6 radical 85 over x minus 36. So this one, you know, I mean, you might remember when you're solving proportions, you typically want to cross multiply. I've been showing you all these tricks and everything, but sometimes you're just better off cross multiplying, because if it gets too ugly, you find yourself in kind of a jam. So that's what I'm going to do here. I'm going to multiply. I'll multiply across the diagonals. So I'm going to take the 6 radical 85 and multiply it by 6 radical 85. That's going to be kind of nice. So, I mean, as nice as 3060 can be. But then I'm going to multiply the 36 by the x minus 36. So if I want to get X alone, well, I want to get rid of that 36. Let's divide that out. So 30/60 divided by 36, somewhat nice 85. 85 is equal to X minus 36. And then if I want to get X alone, I would add 36 to both sides. So $1.21 is what X would be. Yeah, it's not pretty. You know, the computational stuff can be a little cumbersome, but it's manageable. Just it's setting up the proportion first, and that means the most, right? Because if you can set that up, then everything else is just a matter of perseverance. You know, because I mean, you get to a point where it's like, all right, well, what are my different skills? I can cross multiply, or I can do one of the tricks that he showed us. But in the end, that's just algebra or basic algebra. You know, but when it comes to the geometry part of it, you're kind of looking at it like you can't even really get off the mat unless you figure out the orientation of the figures. And like I said before, there are shortcuts, but I feel like it works against understanding. And you know, like people want shortcuts. So what happens? You know, it's like, well, show us the shortcut because I think we would like that more. But it's like, well, then you'll rely on the shortcut and not understand the geometry. Oh, I'm fine with that. I'm not. So here we are. You know, so yeah, that's kind of where I'm at with this. But you can see the diagrams kind of get a little crazy, but it really all boils down to the same skill. I don't want to really beat this to death. So numbers 4, 5, and 6, I mean, they're really the same skill over and over and over again. I don't know why I put 6 examples here. So, you know what I'll do is I'll scratch out the solutions to these so that you have them, but I won't bore you too much longer with this topic because you know it gets a little old and a little dry. So what I did want to get onto was this the triangle similarity proofs, and in many ways they're easier than triangle congruence proofs because you just have to show that two pairs of corresponding angles are congruent to one another, right? It's not a matter of showing SAS or ASA or SSS or you know all those different ways you can go about doing it. It's really just the one axiom: angle, angle. Two pairs of corresponding congruent angles, and that's the end of it. Right. So the first example here is really more of a well, actually, all of these that they kind of anything that involves numerical values, they have the same kind of structure where it's like show it's in proportion, and then from there you can state that it's similar. But the first example are the triangles similar by the AA axiom. Right, two pairs of corresponding congruent angles. Right, if so, name the pairs of angles that are congruent and explain how you know they are. Right, so, well, are they congruent? Well, first we would show that they're in proportion, and then from there we would show that they're congruent. Although this strikes, I know what I did here. It's not my finest hour here. Yeah, this isn't actually supposed to have any labels numerically on it. I think I snagged this from the internet and I forgot to wipe out all the numbers. This is not supposed to be a computation problem. Because I mean, we just spent the last hour going nuts with that. So yeah, that was my bad. Apologies. Typo for somebody though. Oops, sorry. Yeah, so it should look just like this. Angle D and angle B are stated to be congruent to one another. Right, so we have a given angle B is congruent to angle D. And then we have, and again, this goes back to what I was talking about before. If you were to unoverlap, I say unfurl, I'm not really sure I'm using that word right. But if you were to break apart the two triangles, take this triangle out, pull it out, put it over here, and then take this triangle, the whole thing, and put it somewhere else. Would you end up with congruence? Well, maybe, maybe not. One thing I do know for sure is that the angle at A for the small triangle is going to be the same as the angle at A for the large triangle. Right? Those two angle A's are going to be the same as one another. So what I would say here is that angle A is congruent to angle A. There we go. All right, angle A is congruent to angle A, which seems like a really weird thing to say, but if you remember back to the last unit, that's where we got into the thing, the beautiful property known as the reflexive property. All right, so that reflexive property is telling us that angle A, angle A is congruent to angle A, just like 2 is equal to 2. Like you're not really telling us anything that's earth-shattering, but what we're saying is angle A from one triangle is the same as angle A in the other triangle because it's the same angle A, because those two triangles are overlapping. Right? It's kind of like if you stacked a few pieces of paper together and then you cut an angle. Right? But those original pieces of paper were all different sizes. So you have like little notepad paper, little 8.5 by 11 paper, and then you have like a big piece of construction paper. You overlap them, and then you cut an angle coming out. Right? Then you separated them all. Yeah, all those triangles or those angles that you created would all be of different size, but they, in terms of like I'm sorry, not volume, area, but the angles themselves would all have the same measure. So, that's really what it's coming down to, or at least a reflexive property anyway. But what we have here are two pairs of corresponding congruent angles. So therefore, we could say the triangle ADE is similar to triangle ABC by the angle-angle axiom. All right, the angle-angle similarity axiom. All right, so that's like a shorthand proof. It's not really anything overly complicated, but now we get into the beefier stuff. Right, so you can see your statements and reasons, using laws of logic and all that good stuff. But they did give us a piece of information to get us started. Angle W. So my first statement would be angle W is congruent to angle T. And that would be given. Right? We just need to prove the two triangles are similar. And I think this is another instance. I'm almost sure of it. I'm definitely sure of it. I pulled this off the internet also, this diagram, and forgot to get rid of the metrics there. None of that is necessary for this. So, oh, I walked on me. I need to come up with another pair of corresponding congruent angles in order to state that these two triangles are similar to one another. Right? And if I can do that, then we're good. If I can't, then we're not. Right? But we can, because aside from the labels, I did choose an arrangement of triangles that'll play out the right way. So looking at V, you might remember this concept of vertical angles. When two lines intersect, they create vertical angles, right? So we have vertical angles from ZV to W and SV to T, right? And those vertical angles are be congruent to one another. So I can say, for my second statement, angle WVZ, or ZVW is the way I said it initially, but either way, as long as the V is in the middle, is congruent to, you know, pick whichever way you want to go, as long as, again, the V is in the middle, TVS. Right? So intersecting lines form vertical angles, and vertical angles are congruent. All right. I think previously we were saying two lines form a vertical angle, but it does, or it is kind of important. I mean, more than kind of important, it's very important that those two lines be intersecting one another. So it makes sense to say that they have to be crossing in some capacity. Right? They form vertical angles, and vertical angles are congruent. The and allows you to create a conjunction of two statements, and as long as each part is true, the whole thing is true. Are they is it true that intersecting lines form vertical angles? Yes. Is it true that vertical angles are congruent? Yes. So the whole sentence is true. All right. And that's the justification for angle WVZ being congruent to angle TVS. All right. So then I now have enough information, because I just basically said that this angle is congruent to this one. I now have enough information to say that two corresponding sets of angles between two triangles are congruent to one another. So therefore, triangle WVS, VZ, sorry, is not congruent, but similar to triangle TVS. And that would be by the angle-angle axiom. Okay. Now, just as a quick aside, just because it popped in my head just now, because I almost accidentally wrote congruent. If it turns out that two triangles are congruent to one another, then they are therefore similar to one another. Right? Two triangles are similar if they are congruent. But two triangles are not congruent, not necessarily congruent if they are similar, right? Because they could be of different size. But if they are similar, they could also be of the same size, making them congruent, right? So there's a lot of, a whole lot more logic in this course than maybe you thought coming in, right? So logic being the second word of the day. Logic. Word of the day number 2, logic. Right. So then in number 3, we have perpendicular relationship, AB perpendicular to DC, DC bisects ACB. All right, so there's a lot going on there, but I want to get that given into my statement of reasons chart. So AB perpendicular to DC. BC bisects angle ACB. Those are my given. We're looking to essentially show that these triangles are, keep saying congruent, similar to one another. So this triangle and this triangle, right? If AB is perpendicular to DC, so here's AB, here's DC, perpendicular lines form right angles, and right angles are congruent to one, all right angles are congruent to one another. So I can now say that angle ADC is congruent to angle BDC. Perpendicular lines form right angles. And all right angles are congruent. All right, so we covered it all in one shot. I just need another pair of corresponding congruent angles. They did say that DC, line segment DC bisects angle ACB. So here's ACB. It's getting cut into two congruent pieces by that vertical. I got to start using a highlighter here. Not a highlighter, a pointer. So this angle is getting split down the middle. So that's going to create two congruent angles. All right. So I just got to get that into words. So if I know that these two angles are congruent to one another, I can make that statement at least. So angle ACD is congruent to angle BCD. And we just got to think, okay, so what does a bisector do? An angle bisector cuts an angle into congruent angles. I mean, it cuts an angle in half, but if it cuts it in half, those two halves are congruent to one another. So that's a little bit of gray area in terms of the logic of it, in the sense that in theory, we should really spell it out, but it's kind of like what you should do and what I'm willing to accept. So I would say a bisector cuts an angle into congruent angles. And so really the only thing that remains is to make the proof statement. And that is that the two triangles are congruent to one another. ADC, congruent, I did it again. Can't stop myself. Similar to triangle BDC. And that would be the angle-angle axiom. And the consequence of having proved that two triangles are similar to one another is that all the remaining sides or all the corresponding sides would be in proportion to one another, right? So that's a follow-up that we can get into. But yeah, I mean, like I said, we've already kind of beat that to death numerically. But any pair of corresponding sides would then be considered to be in proportion. So if I look at this triangle here, poor quality. Try that again. Just going to grab that. And then its counterpart over here. I'm going to grab that. We know that we have congruent angles and a couple of congruent sides, I would just have to play around with the orientation so that they're facing the right way or the same way. But even still, you don't even really have to do that as long as you have everything kind of in mind. So we have A, D, C. We have B, D, C. So the sides opposite angle D in both cases, in both triangles, would be in ratio to one another. So the sides opposite angle D would form a ratio. So AC over BC. Then the sides opposite the two angles that we determined were congruent. So angle C, that would be AD would be in ratio with BD. And then lastly, the only remaining pair would be CD and, you guessed it, CD. Right? All of these would be in ratio with each other and therefore in proportion with each other. Right? All based off of the fact that the two triangles are similar. We could then say that the corresponding sides of these similar triangles are in proportion. Right? It's an application. It's the ability to be able to reason first and then numerically analyze after. Right? Applications of this, I mean, you see a lot with shadow movement and stuff like that. I mean, the classic example is you have, I'll just talk about it real quick. You have the sun shining down. You have a person standing there that's like 6 feet tall, and he casts a shadow. If you figure out, like how far the person's or how long the person's shadow is, then you can create you can create a proportion or a ratio out of that. So then if there's a building, if the building, there's a building here or a lamppost, I'll go to the lamppost because, scale wise, let's say, I can't draw a lamppost, so I'm just going to say lamppost. You could then use what you know about the individual's height and the length of their shadow to determine the height of the lamppost, right? Because you'd be looking at two similar triangles, overlapping similar triangles, right? But in order to do that, you have to first know that they are in fact similar. So how do you know that? Well, first you got to guarantee that the person's standing upright, right? Or relatively vertical compared to a horizontal ground. Then you'd also have to verify that the lamppost is standing upright, relatively vertical compared to a horizontal ground. And then you have a corresponding pair of congruent angles here because they're overlapping. So then if you know that this individual is 6 feet tall, and you know this dimension, then you would just need to figure out how far the individual is, the end of the individual shadow is away from the lamppost. You'd have to know this piece of information. And if you do, then you could use a proportion to figure out what this missing size is. Right. So, in terms of measuring heights, it seems kind of simplistic, like, all right, well, somebody built the lamppost, so don't they already know how tall that is? Okay, so how about you want to climb a mountain or climb a tree? Like I would personally like to know how tall that thing is. I mean, I'm not climbing a mountain anytime in my life, at least not on purpose, but maybe a tree, is it 20 feet or is it 100 feet? Like, what are we talking about here? So you can figure out this information without having to climb up the tree and dropping a tape measure to the base of the tree in order to figure out its height. These are some things that you can make the determination of. You can determine the height of a height of aircraft. I mean, that's a little trickier because you have a moving shadow in that case, but that's something you can work on. Really anything along those lines. I mean, buildings are the easiest thing to verify. But we'll talk about that more as we go forward because it's kind of a interesting and also verifiable concept. And also we can figure out how fast a planetary object. Yeah, I mean, in the case of you just or in the vein of keeping it as simple as possible, we'll just talk about the sun, for example. You can figure out how fast the sun is moving. And in theory, you should be able to figure that out because you know how long a day is. But based off of the movement of a shadow throughout the day, right? All based off of this basic geometry stuff. And I say basic geometry. The math itself is basic, but the proof part of it is obviously not. Right. So I believe I gave 2 words of the day, so we're good there. I gave the overview, the breakdown, or the nuts and bolts of what was going to be on the test or how it was going to be structured. So I think we're good to go there. That's it for this evening. If you have any questions, stick around. I don't have an assignment for you this week because I don't want to be a jerk and give you an assignment right before you have a test. I know I'm pretty sure I did that last time and I didn't like how that played out for anyone. So yeah, we'll keep it simple this time. So you just have just review your notes, make sure your notes are in good shape, and again, the structure of the test is going to be pretty similar to the last time, where you have a couple of quick hitter questions, fact-based computation type stuff, and then a few tests. Again, I can't say that word. TASKS to complete. All right. So like I said, if you have any questions, stick around. If you came in late, check with me before you go. Otherwise, enjoy the remainder of the evening, and I'll see you all next week.
Thank you, Professor. Have a good
Professor,
week.
thank you. Have a good one.
Thank
Bye,
you.
Professor. Have a good
Professor.
week.
Thanks, Professor.
Have a good week,
Professor.
brother.
Good night,
Take
everyone.
care.
Thanks.
Good
Good
night,
night.
Professor.
Professor.
Hey.
I came in 10 minutes late.
All right, I get you.
Okay. Bye.
Thank you.
Thank you. Bye. Have a good night.
You too. Take care.